we've talked about different shapes and solids in 2 and 3 dimensions, but we haven't talked really about the kind of ambient setting, if you want, that these shapes are living in. So things like the plane, if you're a 2-dimensional shape, or in kind of 3 dimensions, if you are a solid. So what we want to do now is to really carefully quantify these spaces. And really, I'm purely going to focus on the 2-dimensional case, so the plane. And once we've quantified things, we are going to be able to describe these shapes potentially with much greater precision, if you want. So this is what coordinate geometry is all about. And really what I'm going to describe is Cartesian coordinate geometry, named after René Descartes, who realized there was a way to numerically describe positions in the plane very accurately, or in a very, very powerful way. So when we talk about the plane, it's just a plane to begin with. It's a flat plane. If we want to describe a position in it, we need to, well, decide how to do it. And this is our basic approach to describing positions in the plane. So we draw 2 straight lines, which are at right angles to each other. And these straight lines kind of go on forever if you want. I'm just going to do this. We label one of them the x-axis, that's the kind of the horizontal one. We label the other one the y-axis. And we really think about these as 2 number lines. So when I think about a position on either the x-axis or the y-axis, I think about that with a number, if you want. And the way you think about it kind of in terms of orientation is you think about, let's say, the number 1 on the x-axis as being, let's say, here. The number 1 on the y-axis as being kind of here. And 0 on both axes is exactly the cross point, often called the origin or the center. So if I give you a point in the plane, let's call it P, how might I describe this point numerically, given this kind of decision about drawing these 2 lines at right angles to each other? Well, notice if I take this point, I can drop a vertical line down to here and a horizontal line across to here. And that's going to give a position on the x-axis, a position on the y-axis. They're going to correspond to 2 numbers. Let's say A here and B here. So here's the plan. I'm just going to describe P numerically as an ordered pair of numbers. And I'm going to write it, open bracket A, comma B, like this. Now this is not to be confused with interval notation, which is something that you've got to be kind of careful of. This is us describing a position in the plane using coordinates or Cartesian coordinates. So when we write this, this is P, if you want, expressed in Cartesian coordinates. Cartesian, as I said, after René Descartes. There are other coordinate systems, other ways to describe positions in the plane. You may have heard of them. Polar coordinates is an example, but we are going to focus purely on this one. So this P is just a point in the plane. Now the plane now is just flat, okay? But because of the fact we've fixed these 2 axes, these 2 kind of horizontal and vertical numerical things, we're going to call this the xy plane. It's kind of our mathematical notation. So this, if you want, is a mathematical model for the plane. So it's kind of a toy, it's a model for what the plane is. Well, so it's kind of an idealized version in our minds of the plane. Now this is the setting that 2-dimensional geometry occurs in. If I give you a triangle or a circle, I can sit it in the plane in all sorts of different locations. Now, something we've talked about kind of broadly is the concept of, let's say, length, for example. And intuitively, let's say the length of a straight line is how long is it. But imagine if I give you 2 points in the plane and I say, what is the length of the straight line which joins the 2 of them? So that straight line would often be called the distance between the 2 points, or the length of the straight line. Let's kind of think about how we could actually calculate that. So my first aim is to determine the distance between 2 points. Determine the distance between 2 points. All right. So let's take this. Let's take this again. In fact, what do I do? Let's draw a picture. Let's do it again. Let's make it a bit smaller though. So we've got the XY plane. And let's take 2 points, let's say there and there. So we'll call this first one, let's say P1, which is equal to, we'll say X1, Y1. And we'll say this down here is P2, and this is X2, Y2. All right. What is the distance? Well, intuitively, it's just going to be the length of that straight line, isn't it? It's the length of that straight line. So the length of that is equal to the distance. That's what I mean by distance. Now, how are we going to calculate that? So, notice, at least the way I've drawn it, this guy, I can think about it as a hypotenuse to a cleverly chosen right-angled triangle. Namely the following: if I draw a horizontal line across here until I hit that, and a vertical line here until, let's try this again, a vertical line here until I hit that. Let me try this one more time. If I draw these two lines, and let's make this a right angle, well, what do I know? I know that the length is the length of a hypotenuse of this right angle triangle. So if I know the lengths of these two sides, then I'm going to be able to calculate the length of the hypotenuse, so the distance between the two. Now let's think about this a second. This guy here, what's the length of that? Well, from the way I've drawn it, it's the y1 coordinate minus the y2 coordinate, right? It's y1 minus y2. But I may have drawn this the way around. y2 may be bigger than y1. So it's a bit of a mess thinking about this business. Why don't we just bring in the big guns, which is the absolute value. So the length of this is the absolute value of, let's say, y2 minus y1. Doesn't really make any difference, because the absolute value is the same as y1 minus y2. So this completely removes the issue of which one is bigger. Remember when we talked about the distance between 2 points, right? Your first approach was you take the larger one minus the smaller one, but then, well, that's a bit of like, what if I'm not sure which is larger? Well, then you can use the absolute value. Same thing here. What's this length? Well, it's going to be the x-coordinate there minus the x-coordinate there. Let's not worry about which is bigger. It's going to be the absolute value of x2 minus x1, no matter what, regardless of which is larger. Awesome. So what does Pythagoras tell me? Pythagoras implies the following. It implies, well, let me just remind us what Pythagoras is a second. It says that the hypotenuse squared is equal to the sum of the squares of the two sides. So maybe I'll do it as height squared, or maybe length squared. Yeah, width squared. Width squared plus height squared in a right angle triangle. Well, I want to know the length of the hypotenuse, so I just take the square root, don't I? Everything's positive, so makes sense. So it's going to be the square root of these two things. Nice. So let's just write that in this case. It's a little off to the side, so this implies the distance between x1, y1 and x2, y2. What's it equal to? It's equal to the square root, I'll write it pretty big, square root of, well, the absolute value squared, but that's just the same as the actual term squared, so let's do x2 minus x1 squared. So you don't need the absolute values because you're squaring, so it's always going to be positive anyway. y2 minus y1 squared. Awesome. That is often called the distance formula. And it's important you internalize it, remember it, but you should definitely know why it's true. And it's true because of Pythagoras. There's a version of it in three-dimensional coordinates, so I haven't really mentioned anything about three-dimensional coordinates, and I'm not going to, because it's something you'll study after your first calculus classes. But the essential essence is there's a third axis, the z-axis, or the z-axis, and the distance formula is the same, except you'd have a plus 1 z2 minus z1 squared, so it's very, very similar. Okay, very nice. So let's do an example to make sure we fully understand how this could be applied. So example. So let's do kind of an interesting one. Let's do describe algebraically. Describe algebraically. So what do I mean by that? Well, I'll tell you in a second. All points x, comma y, which make up the circle, making up the circle of radius 4, centered at, let's say, 3, 1 in Cartesian coordinates. What do I mean by algebraically? So what I mean here is it's by an expression or an equation in x and y. So this is the kind of thing when you're looking like, what's the circle got to do with this distance formula business? Like why are we doing this after doing the distance formula? Well, let's just think it through real careful. So picture. I think when you're doing geometry or anything geometric, it's a very good idea to always draw pictures because you should be thinking visually a lot of the time. So let's draw the xy plane. Let's draw the central position, 3, 1, which is about here maybe. And let's draw the circle. The circle is radius 4, so it's going to look like what? I don't know. Hopefully going to look better than that. So radius 4, so it's going to look something along these lines roughly. Doesn't need to be perfect, just want some idea. So that's what the circle looks like. Now I'm interested in what? I'm interested in the xy which make up the circle. So I'm looking for basically positions x, y which make up the circle. Now what's the crucial thing about a circle? A circle by definition is all the points which are a fixed distance, the radius, from some given position, the center. So if I'm on the circle, that is precisely the same statement as saying that I am distance 4 from 3, 1. So by definition of the circle, x, y is on the circle if and only if it's distance 4 from 3, 1. So let's just write this down carefully. So x, y is on the circle, centered at 3, 1, radius 4, if and only if the distance between x comma y and 3 comma 1 equals 4. Well, that's if and only if what? Well, the distance between x comma y and 3 comma 1 is, well, we can use the distance formula. Pretty nasty mess. Let me try and do this more neatly. If and only if the distance, so that's what the distance formula is, x minus 3 squared plus y minus 1 squared, that is literally the distance formula above, is equal to 4. But everything's positive, so this is if and only if. Well, let's square everything to get rid of the square root. X minus 3 squared plus y minus 1 squared is equal to 4 squared, which is 16, but I'm just going to leave it as 4 squared. Now, notice the following in this formula. This formula has the information in it of the center, first of all. The center I can see, it's the 3 and the 1 there. Right, that's telling me the center. And the radius, I'm seeing it in the square of this side. So it's not a huge leap to guess what kind of the general story is here. So the general case is, unsurprisingly, x comma y is on the circle, or centered at, let's say, a comma b. Centered at a comma b, radius capital R, if and only if, you guessed it, x minus a squared plus y minus b squared is equal to r squared. That is the general formula. And a special case would be so x squared plus y squared is equal to r squared. That's a special case, right? It's centered at 0. Or 0, comma 0, which is the origin, which is the crossing of the x and y axis. The origin. Now, there's something very interesting about this, because a circle is this beautiful geometric object, okay? And here is a piece of just cold algebra, right? It's an equation involving unknown numbers, variables, which is just a piece of algebra. And the two are basically linked, they're the same. So this is really where geometry and algebra are truly related in this coordinate geometry approach to describing shapes. So this is an example of the following deep relationship. When I say deep, I mean it's how do I put it? It's got mysteries in it that are beyond all current human understanding, which sounds crazy, but it's really true. There are questions within what I'm about to describe which we have never truly mastered, and things that the Greeks asked that we still haven't been able to answer, and perhaps never will. But the relationship is the following. If you have a piece of algebra, let's say, so when I say a piece of algebra, let's take something simple. Let's take just an equation involving x and y. Involving x and y. Something like this, for example. Well, any equation in x and y has a natural geometric partner, namely all the positions x, y which satisfy the equation. So given any piece of algebra like this, there is a corresponding piece of geometry. corresponding piece of geometry, and as I said, it's the shape, if you want, in the xy plane given by points so I'll write it like this, let's say capital A, capital B, such that if I set x to be equal to capital A and y is equal to capital B, that satisfies the equation. So given any formula involving x and y, so should I say any equation involving x and y, you can ask yourself, well, what are all the points that satisfy that equation? What are all points that satisfy that equation? And that's going to give you some sort of shape, something or other, some sort of curve, who knows, within your space, within the xy plane. And asking yourself what the shape looks like given a piece of algebra is really amazing, or a really interesting question, because I mean, if I just give you some formula involving x and y and say, what's the shape corresponding to this, what's the piece of geometry, it's really not obvious. You can use a computer, but it's not necessarily going to really tell you about the detailed behavior of it. And this is a scenario where basically the algebra may make it very non-obvious what the geometric shape looks like in the sense that if I gave you that cold and said, okay, describe to me all the points x, y in the xy plane which satisfy that condition, the fact it's a circle is not obvious at all, right? The fact that this gives a circle centered at a comma b, radius r, in my opinion, is highly non-obvious. So you can imagine if I give you some more complicated expression, it'll give you some sort of shape, but it's not at all obvious what it is. Now you can try and plot it with a computer, but it's a very very numerical approach to it. Understanding the relationship between these two sides is really kind of one of the big goals of mathematics. All right, so I've rattled on enough. We don't need to understand this in a huge amount of depth, but let's do an example that is useful to understand pretty well. And you may be thinking this is related to graphs of functions. If you're kind of thinking ahead, it is. It's very closely related. It's something we're going to study when we go on to functions. But here's an important example. A really important example is if I give you an equation, let's say of the form ax plus by is equal to c. And when I write these, I'm going to assume that a, in fact, let me do this slightly differently. Let me use lowercase. Let me do ax, because I don't want to get it confused with my statement in the box. So let's do ax there. Okay. So a, b, and c here are constants. That are some fixed numbers. If I look for the x comma y that satisfy that, I get a straight line. Now this is not obvious, but it's a very beautiful fact. So anything of this form with a, b, and c constants, the x, y that satisfy it are a straight line. In the xy plane. Now here's a really good illustration of this, or at least an illustration of a piece of algebra that we should all know and maybe have seen before, but I kind of think it's a nice place to see it here. So here's an example of this. So imagine I have two straight lines and I want to know the intersection. So that's the point where the straight lines cross each other. So find point of intersection of the two straight lines so I'll give them in this format. Let's do x plus 2y is equal to minus 1 and 3x minus y is equal to 2. Let's do this. Now we want to find it precisely, so we could graph these if you want, or draw them using a computer. And I think, I mean, this isn't too important, but I think what it's going to look like is if you were to draw the xy plane, and you were to graph these two guys, you would end up with something, I'm not exactly sure, something along these lines. Something like that, and kind of something like this. Something along those lines. So we're looking basically for this point here. What is that point? So what I'm going to describe to you is a way to do this without actually having to graph or plot these things and kind of looking at it. So we want to know this precisely. So it would be no good just to get a computer to draw a picture and then to say, oh, it's roughly there. We want to know exactly what it is. So what do we need? Well, we need an x, y that satisfy both of these equations simultaneously. So we need x and y such that, okay, so x plus 2y is equal to minus 1 and 3x minus y is equal to 2 at the same time. So this is an example of two simultaneous equations in x and y. So it's important that we are able to solve a system like this because they kind of turn up quite frequently. And it's nice that we can think about it geometrically as an intersection of two lines, but let's try and solve this algebraically. So here's the basic approach to doing this that I would recommend. So first of all, if I had an equation in one variable alone, then I would hopefully be able to solve in that variable and it would give me an answer. But the thing is, I've got two variables. So what I'm going to do is I'm going to try and eliminate one from the other by using, or eliminate one of the variables from one of the equations using the other equation. So here's the basic plan. Let's solve one equation in y. Or it could be x, but let's just do y. So let's do, I don't know, let's do the first equation. So rearranging this would give me what? It would give me y is equal to minus x minus 1, all divided by 2. So that's just a piece of algebra rearranging to get y on its own in this case. Now what's the next thing I should do? Well, let's take this knowledge and substitute it into the other piece of data, which is the second equation. So let's now go over here, do this properly, maybe. Let's go over here by substituting in the second equation. So what does that give me? Well, in the second equation I would get 3x minus y, so that's now minus x minus 1 divided by 2. You've got to be very careful with the algebra here, is equal to 2. Now notice now I have an equation involving only one unknown, namely x. So let's solve this in x. So solve an x. And I could do this the other way around, but this is a perfectly valid way to do it, so let's get it done. So we've got now 3x minus x minus 1 divided by 2 is equal to 2. So this is if and only if. So let's kind of unravel this. 3x, okay. So minus is a plus. It's going to be plus x divided by 2. In fact, I'll do plus half x. Minus is a minus, so it's going to be minus a half is equal to 2. So now let's combine the x's. So that gives me 3 plus a half, that's 7 over 2 x. Then it would be 2 plus a half. So 2, oh sorry, it's 2. Oh, no, I'm wrong, aren't I? It's a minus there and a minus there, so this should be a plus. Ooh. It's easy to make a mistake if you're not careful. So then it would be 2 minus a half, that's 3 over 2. So finally, rearranging, x is going to be equal to 3 over 2 divided by 7 over 2. That's 3 over 7. Nice. I've got one specific value of x that works. But remember, I'm looking for the whole coordinate point. Just knowing the x is no good. I also need to know the y. Oh my goodness. So now all I've got to do really is just to take this value of x and work out the appropriate y. So substitute value of x to find y. Substitute the value of x to find y. So what was it? Well, let's just go back to this guy. This is the easiest. You could really do this anywhere, but that's a nice choice because we know y in terms of x. So now y is equal to minus x minus 1 divided by 2. Goodness. But that's now equal to minus 3 over 7 minus 1 divided by 2. So this is a nice piece of algebra. So this is minus 10 divided by 7, all divided by 2. So this becomes what? It's going to be 10 divided by minus 10 divided by 14. You can take it a factor of 2, minus 5. Minus 5 divided by, in fact, let me get my head straight, minus 5 divided by 7. Nice. So what does that tell you? Finally, this would tell us what the point of intersection is. So the conclusion is the lines, oh my goodness, sorry. Lines meet at the position, what is it? It's 3, 7 divided by 5, 7, minus 5, 7. Fantastic. So this is an important example, both from a geometric standpoint, but also from the standpoint of algebra, because it illustrates a key way of solving simultaneous equations, namely taking one, solving it in one of the variables, feeding that into the other equation, that gives a single variable equation, solve that to get one of the values and then feed that back in to get the other. So this is a really important piece of algebra.